So you have seen this diagram before, isn't it? So this is what you call a op amp. And you already know the basic characteristics of op amp, which is that it has, what is it? What are the basic characteristics of op amp? Andrew, who is Andrew? Where is Andrew? Yeah, what is the basic characteristic of op amp? It amplifies, but is it a very good amplifier or a very bad amplifier? Or is it a too good amplifier? Is it a bad amplifier? Is it a good amplifier? Or is it too good amplifier? Yeah, exactly. How you wear it up, you know. So basically, if you just talk about the op amp itself, it is too good amplifier. Why is it too good? Huh? Exactly, because its gain is infinite almost. So if you apply a small variation between the two inputs, which you call V, you can call VID, between V in minus and V in plus. If you apply a very small voltage, it will amplify it to a very large output signal. And if it amplifies to a very large output signal, what will happen? Will you get that large signal? Say you have a very small signal, few milliamperes or millivolts, you know, or say few microvolts, and your gain is close to infinity. You know. So your output voltage will be how much?
What was the question?
The question is you apply a very small input voltage, say a few microvolts,
Right.
and the gain is very large, close to infinity. What will the output be equal to? Will you get it?
No.
What will you get?
Plus infinity?
Whatever.
Will you get it?
Infinity?
Will you get it infinity out the output of your op amp?
No.
What will you get?
I don't know.
What will you get?
Would you get like clipping voltage?
Exactly, you'll get clipped, you know. So clipped to what?
Your rail voltages.
How much is that?
Depends on how much voltage you put in, but it'll be the output of your.
Yeah, so it's clipped to a certain voltage. What is that clipped voltage?
Close to the supply voltage.
Yeah, what is that clip level, you know? What is the clip level, you know? Where is the clip level is related to which voltage? The clip level of the op amp is related to which voltage?
Input.
No, because the input is very small and your output is very large, supposed to be very large, but somebody said here that it gets clipped. So my question is clipped to what?
Just what?
You're close, it's getting close. Who? Come on, somebody should be able to answer. Okay, do you want me to give you a hint? Okay, a op amp also have two
Your supply rails, your.
supply voltages,
Yeah.
VCC and VEE, which is say approximately say plus 15 volt here, in this case, specific case, and minus 15 volts here. So it gets clipped to what? Exactly, clipped to that. You know. So if the output goes very large high, it will get clipped to this. Or if the output goes very large low, it will get clipped to this. You know. But not exactly this. It gets saturated to a voltage which is closely related to this voltage. Usually about 90% of it. You know. So how much is 90% of 15 volts?
135.
13.5. So you will be clipped to 13.5 or minus 13.5. Why is it not exactly 15 volts?
Because life isn't perfect, so it's missing.
And that's a good question, good answer. Life isn't perfect, you know. So what it also means that your transistor circuits are not perfect, you know. all the transistors that you use to build op-amps have got to have certain voltage drops in there. Okay, so between the collector and emitter, there will be a transistor here, there will be a transistor here, there will be drops across them. Okay, so those drops will eat up part of your headroom voltage, and instead of getting 15, you'll get 13.5. Okay. So since the op-amp actually clips the voltage, you apply small voltage, it clips to high or low. So is it a good amplifier? It is not, isn't it? It is really not a good amplifier. It is a too good amplifier. So a op-amp is really not an amplifier really that much, you know. Just by itself, what you can characterize op-amp as? What? The op-amp should be, just by itself should be characterized as what? Just by itself. Without your resistances which Fakul showed you, remove them. Just the bare op-amp. It should be called what? Should it be called amplifier? Not really. What should you call it? Huh? What should you call it? Something that goes all the way up, all the way down for small difference. If this is slightly higher than this will go down. You know, if this is slightly higher than this will go up. So what should you call it?
Balancing pair? Balancing pair?
No, balancing pair has nothing to do with this. Balancing pair? You know, everything is used. You use semiconductor to build everything. You know. This is simple, very simple. Who can say? Who can say? Come on, quick.
It almost acts like a digital repeater.
Huh?
It almost acts like a digital repeater.
Yeah, that's close. That's a close answer. Who can give me the correct answer? That's very close, you know. Coming close. You know.
Yeah, no, well, doesn't matter. This will be different. Would it be a short?
No, it's not short. You know, it's going to short means zero voltage. You are not getting zero.
Okay.
No. Okay. Should I give you more chance, or should I just pronounce myself?
Pronounce it.
It's a comparator. Between two inputs, you know, it's a comparator. Compares between two inputs. Whether this is larger or this is larger, that's all it's doing. So when you have an amplifier which is very high gain, it works more like a comparator rather than an amplifier. Okay? So it's a comparator. So that is the title. What I told you before when I started the lecture, I told you that I'm going to discuss the op-amp as a comparator. So I already uttered the word and you didn't catch it. So this is a comparator. Okay, so this is what? Op-amp as a comparator. Op-amp as a comparator. Okay, so that's the topic that we are going to discuss this week. Okay, so what is the symbol of this? Do you know? What is the sign of this terminal? This is plus, this is minus, this is plus. This is what is the sign of this terminal? It doesn't show in any textbook, but it must have a sign. What do you think the sign is? What is the sign of this terminal?
Current always travels from the
What is it? Is it plus or is it minus? Pick one.
Minus. Yeah,
So the sign of this thing, which no textbook gives, is actually a plus.
get up here. Just grind
It's
out.
understood that is a plus. You know. So that means the relation between this terminal with this terminal is plus. That means if this goes up, this will go up. If this goes down, this will go down. And the relation between this and this is 180-degree difference. If this goes up, this will go down. If this goes down, this will go up. That's the relation. Okay. But does the op-amp always have to have one output terminal? Does it always have to have one output? Does it have to have only one output terminal in general? Say amplifier. Does the amplifier have to have just one output terminal? Can it have more?
I'm going to go with no because you're asking. It seems we haven't learned about them having more than one, so I'm going to go with yes, they can in weird circumstances.
It's not weird, it's a normal circumstances.
Normal circumstances, I'm sorry, couldn't judge the same.
So you can actually have, but you usually don't need it, you know. You can have, in many cases, particularly in integrated circuits, you can have a minus here, a plus here, and then you can take 2 out of here, okay? And then this is the plus here and the minus here. So when you actually have experience of building the transistor circuit of an op-amp, you'll see that it will naturally come with 2 outputs. It will come out with a positive and a negative at the output. But what you do is that you actually convert the 2 terminals into 1 terminal. You know. From a differential, so this is the differential output. Differential output. And this is a differential input. And in this case, this is a differential input. And what is this? What do you want to call this? Hmm?
A differentiator?
No, this is a differential input and a differential output.
And inverter?
What would you like to call it?
Just that.
This has got 2 ends. How many ends this has got? This has got 1 end here, 1 end. How many ends it has got? This one output is how many ends? 1. So what should you call it? What is the other word for 1?
Singular.
Single. Okay. Then what should you call it? Single. Single-ended out. Single-ended out. So we are not going to work too much with this. We are going to work mostly with comparators based on 1 output. So let's look at how does a op-amp stops from behaving like an amplifier and becomes a, what is the limiting case of a op-amp behaving like a comparator rather than a amplifier. Okay? So say for example you have a op-amp, say a non-ideal op-amp. A non-ideal op-amp will have a gain of how much? Will it have infinite gain? Non-ideal op-amp? It will have some limited gain, isn't it? So say its gain is limited to 10 to the power 15. 10 to the power 15. So this is 10 to the power 15. 10 to the power 5, say rather. 50 is too large, you know. 10 to the power 5, and it has got supply voltages plus V, C, C, and say this is equal to whatever it is, and this is minus V, E, E. Now you might wonder why I call it CC and why I call it EE. If you look at all the textbooks, it call it, one of them will be called VCC and the other one will be called VE. Do you have any idea why it's called like that? It's okay if you don't.
Cathode?
You're not there, but just close, you know. It is because C goes with the collector of a transistor and E goes with the emitter of a transistor. So it is connected to the collector of a transistor, you know, in the top. and this is collected to the emitter of a transistor. So when we discuss transistor, you will know more detail. You already know transistor, emitter base collector. You know,
Oh, I personally don't know.
some people know, isn't it? So if some of you may have taken electronics as a subject in high school, so you may know a little bit. So that's the reason it's called CC, and that's the reason it's called EE. Okay? So now you take this, okay, say this is the negative terminal and this is the positive terminal, and you connect the positive terminal, say, to ground, you know. Okay? Yes?
Why is it CC and EE and not just C and E? If it's just collector and emitter, where's the extra letter come from?
That's a good question. It has been traditionally like that. Now, if you say VC, if you say just VC, then it will mean just the collector, the voltage of a collector. So I would suppose CC would mean that it is the top voltage of a system, bipolar system, the uppermost voltage, you know. And EE, by tradition, it has been called like this, EE. That EE is the lower potential. CC, maybe it's a EE, the lowest E. Maybe you will have maybe you have E's in between. This is the bottom E, so it's called EE, the final EE, and the CC, the final on the top. Maybe for the reason I don't know. Okay. So say you have a setup like this, and you have output here. Okay, V out, and you have a V in here, and the difference is how much? This is called VID. VID equal to how much? If this is grounded, how much is VID? Input difference is how much? V. Yes. Okay. So for this amplifier, can you calculate the input voltage? Okay. Okay. Determine equal. Say this VCC is equal to plus 15 volts. And this is equal to minus 15 volts, and V sat plus, we'll call a quantity V sat plus, which is the top upper saturating level, and you will call V sat minus as the lower saturating level, and this we said this is equal to 0.9 into VCC, and we call this equal to 0.9 into VEE. With the negative sign. So how much is this? 13.5? V set plus how much?
13.5.
13.5, okay. 13.5 volts, and this is equal to minus 13.5 volts. Okay. So it will saturate to that voltage. It won't go up to full 15 volts plus or full 15 volts minus. Saturate to that voltage. So can you plot? Can you find out the value of V for which it will saturate? That means go to the maximum level, top or bottom. What is the value? So if you put V in something positive, you know, then this is larger than this, so it will go down, isn't it? If you put something negative here, then this is larger than this, and this will go up. Correct? So then, can you draw a curve for me showing as the V goes from positive to negative, what is the output look like? So you draw me this curve. V in, V out. Okay. So it will be a curve. You know, when your V in is going positive, this is going positive, this is negative, large compared to this, so it will go down. Okay, so it will go down, it will be somewhere here. And if it is negative, then this will be smaller compared to this, and this will go up, so it will be somewhere here. Okay, so this will be limit here, which is 13.5 volts. This will be limit here, which will be minus 13.5 volts. Okay. So can you draw this complete diagram for me? So what will happen between here and here? How much is this voltage? How much is this voltage and how much is this voltage? Can you find it for me? What was your name again? Shreyas. So Shreyas will show you how to do this.
The whole calculation?
Yeah, show everything, We don't hide anything here.
Second 3 lines.
Okay.
It's not even 3 lines.
It's heavy, mate. I'm gonna get it all right.
You finished? You done? The same thing on the other side.
Just using this equation?
Yeah, very good. So just use the gain equation, V out by Vn equal to this. And this will give you this amount, which is 135 microvolts. Yeah. Sorry.
No, I got you 4.
Microvolts. Okay, so as you can see here, that for a very small voltage, within this range, within this range, it is. What do you call it? What do you call it when you have a straight line connecting 2 points? What do you call it? Linear. Okay, linear. This is the linear region. Of the op-amp. So you can see the linear region is so small, even for a gain of only 10 to the 5. So if you have an infinite gain, what will happen to this card? Who can draw that? If you have infinite gain, this card will look like what? Somebody from the back who can show me. If you have infinite gain, what will happen? This car will become like what? Okay, over there, next row. Very good. So it will become like this, So the higher the gain of the op-amp, the more it is like a comparator. So in the extreme case, yes.
Doesn't that require infinite slew rate? What you've got going on now?
Yeah, we need infinite slew rate, exactly, yeah. So you have to be very fast move, yeah. But we are going to slew rate in this lecture, in this class. This we restrict ourselves to very basic concepts, okay? So this is going to be the shape of your op-amp. This we should call what? Voltage transfer card. Okay, this is the voltage transfer card. Yes?
So are those 2 lines there both straight? The one at the top and the one at the bottom?
Yeah, straight.
Yeah. So what? If they're just straight all the way up to here, what's this? What are these arbitrary points here?
These arbitrary points are when you have a gain which is not infinite. So when you have gain not infinite, you will have some linear region.
But when it
As the gain increases, it will gradually, this line, dotted line will gradually move this way, this dotted line will gradually move this way, until that merges into this one straight switch. Okay? So the dotted line, this dotted line will gradually move this way as your gain increases. And finally, you will have just this line will just override this line, override on this path. So you've lost your linear region. So it's just a switch, comparator. Okay? So this is a curve between output voltage and V in, input voltage, V out and V in. So we call it a voltage transfer curve. Okay, we call it a voltage transfer curve. What other curve can you draw for a comparator? You can draw another curve like this. So in this you had an axis which is V out in the y-axis. You also had an axis which is V in the x direction. What you could do is that you could do another plot where you have still two axes, but this axis is volts, which is both V in and V out, and also V in on this axis. Okay, and then this axis, what should it be? What should this axis be? The x-axis be? All voltages occur in what? Do they occur in space? Do they occur in what? Who said that? Time. Exactly. They occur in time. Everything happens in time. Is there anything which doesn't happen in time? Everything. So if you're changing your voltage, it's happening in time. Okay? And since this axis is free, so this will be time. Okay? So you have time axis and your voltage axis. So the output voltage, because it is like a comparator, the output voltage will swing to full voltage, this, or full voltage this. So it depends on input voltage. So input voltage, if you look at this circuit here and plot this here, say I have got a input voltage, I will draw the input voltage, then you draw the output voltage for me for that circuit. Okay? So my input voltage, is there a limit to what it can be? Have I got any limitation to what in imagination what Vin can be? It can be anything, isn't it? So I can just close my eyes and draw whatever, and that will be my input voltage, isn't it? So I can draw like this, like this, like this, like this, like this, like this, like this. This is my input voltage. Okay. Can be anything. Okay. Doesn't have to be a sine wave. So this is your V in time. So it goes above 0. So this is your 0 volts, and this is, so you can plot here 0 volts. Then you can say this is your 5 volts. Then you can say this is your 10 volts. Okay. Then you can say I think it's too large here. Just it's not out of scale. So this say you have your 30.5 volts here plus, and you scale out like this here and say this is your minus 13.5 volts. Okay. So this is your V sat plus, V sat plus, and this is your V sat minus. So who can draw the output voltage for me for this circuit? If that's the input voltage, who can draw the output voltage? Who? Somebody pointing to somebody. No, he has done once.
No, the guy in the yellow shirt.
Who is the guy in here? No, he has done already. He has talked already enough, equal opportunity. Everybody needs a chance,
No.
Okay,
Yeah,
he's
that's what I
going to
thought. I was
volunteer.
thinking
What is the
maybe-
name again?
Scott.
Scott. Scott will draw it for you.
Thank you, Scott. The relevant VR. Thanks, Scott. So we're going infinite.
Yeah, so you can't go infinite because you saturated here,
Yeah.
up to here. So as your input voltage is below 0, goes above 0, again goes 0, what is your output voltage?
Yeah. Are we going infinite gain?
Yeah, infinite gain, exactly, yeah. Infinite gain.
So,
No. See here, look at this circuit here now. If your input voltage is negative, then this is smaller than this. Yeah. Yeah, it'll go on and until that. Every zero crossing. Yeah, should be 0%. Okay, very good. Yeah. So this is your behavior between input and output. So your input is going this way, and this is a V out. V out T, okay, is like that. And you're considering infinite gain, a comparator. So it goes up, down, up, down. Okay. So this amplifier, op amp, calculated like this, can be used to detect what? What can you detect in the input by using this comparator? What can you detect? What can you detect in the input? What kind of detector can it be? What can it be used for? To detect what? Anybody? Exactly. You can call it, a better term is zero crossing detector. Zero crossing. You can call this zero crossing. So this you can call this, if it goes 10 to the power, say 2, no, it's large enough, isn't it? Okay. So this one is a zero crossing detector. Okay. So now we know a bit more about the behavior of the op amp. That it's really not a amplifier, it's really a comparator, and it can be used to detect signals levels, whether it is crossing 0 or 1 or some other level. Okay, so next is, how do you use it to detect a level which is not 0? So you want to detect a level which is, that you are not trying to detect level 0, but you are trying to detect another level. What can that be?
Really low.
No, the brain is still high. Op amp, you can use it to detect a voltage level which is not 0, a positive voltage, isn't it? So we can now erase this whole thing, erase everything here, erase all of this, and call something else. What is that? Positive reference detector. Okay, positive reference. Positive reference detector. Okay, we can make a positive reference detector. That means the voltage you are trying to check is not whether it is at ground level, but a level which is a positive value. Okay, so you would actually go and do the same thing here. We redraw the same thing, and we don't say any more 10 to the power 5 or whatever. We know this is a comparator, and which is a very high gain, so we don't have to say that thing again. and here a negative, and here is positive, and this is your V output, and this is your V input, and this time you are trying to detect a positive reference voltage, a positive level. So are you going to connect to 0 anymore? What are you going to connect? Some positive value. Okay. Hmm?
So would it be the level you want to check for?
Yeah, exactly. We want to check for a positive level. Okay. So we want to check for, you could put whatever, 5 volt, 6 volt, 10 volt, whatever, whatever makes sense, So you can call it V ref plus. Okay. V ref plus. Okay. Again, for this V ref plus, with V in here and V out here, you can again draw two things. What are those two things you can draw? You can draw this and else, and you can draw this. Okay. So let's erase all of this. Okay, and let's erase all of this. But before we completely erase everything, I forgot to say, what should we call this curve? Where you plot voltage against time, what should you call it? That one you call voltage transfer curve. What should you call this one? Voltage time, yeah, there's voltage time, but we call it transient curve. Okay, so we'll have one transient, one will have voltage transfer. So for this one, if we again try to plot, so we'll have an input and the output. We'll have V out here, and we'll have V in here. Okay, but there's a reference here, voltage reference. That means this reference you compare the input. So some triggering will happen at that voltage now instead of 0 voltage. So where should we put it? You should put it here or where? Where should I draw it? And how should I draw it? VREF, how should I draw VREF here? In this voltage input and voltage output plane, where should I put VREF? It can't be here, isn't it? Because it's negative. So it should be somewhere here, isn't it? So what should I do? What do you want me to do? Should I draw a straight line which is indicating value of VREF? Do you think it's a good idea?
Yeah.
Yeah? Everybody? Should I draw a line here saying that is VREF? What do you think? No? You agree? You don't agree? So then you tell me what should I do? You agree or disagree? We agree, okay, you agree. So I'll draw, he agrees, so I'll draw, I have permission from him to draw a line here, see. But I'm going to draw a broken line, a pseudo line, not really a line, like a line, but which is indicating there's a line here, and this value is V ref. This is V ref plus. So if you draw geometrically a line whose value is V ref plus, then that line would be like this, straight line, because input is equal to, you're comparing the input to V ref, but you don't know the output how much it will be. It can go, that depends on what you get in the output here, isn't it? So as your input is going, input is traveling on this line, isn't it? From negative to positive. So what will happen? Who can draw this one? The voltage transfer curve for this positive reference. Okay, and then we'll take a 10 minutes break. So the faster you can solve it, the faster you'll go to break. Jonathan, who is Jonathan? Yeah. Doesn't matter, anybody can do it, you don't have to be correct, We have a lot of people here. Jonathan, we have John, we have Andrew, we have Sean, Yeah, you draw the output, and the input moves from here to here, where the output moves. So V out plus, I give you a hint, you know. So V out plus, V set plus is here, you know. V set plus is here. I take the same length and go up to here. This is V set minus. So these are the two levels, okay? So you have VCC, VEE, and for this you have V set plus here, and you have V set minus here. So this is the limit, saturating limit of the output. So as your input goes from a negative to positive voltage, what will happen? Yeah. So input is say VREF. From negative, this is a positive voltage. You see, this is a positive voltage, and this input is starting negative. Yeah, it's down here. So output will be what? If this is smaller than this, if this is large, output will be what? High or low? Help him.
So down here.
It would be so the negative is more than the
Yeah, he's starting from a negative input voltage. So you see here, look at this diagram. If you have a negative voltage here, and this is a positive voltage, okay, this is positive relation with this. If this goes up, this goes down. You see. So if this goes, if this is going down, you see, this is smaller than this, then this will go up. So where it should be?
Should be at the top.
No. You start from the bottom, but your output should be at the top.
Yeah.
So like that.
Yeah.
There's no curve here. There's only in the time domain, you see. In the voltage transfer curve, everything is straight. You're going here, your input is on this line, you see.
Stop lines.
Your input is on this line, you see. Your input is on this line. You have negative input to positive input.
So like
Output. Yeah. No. Okay, go ahead then. No.
Set your voltage reference point. That's the reference.
I want to help, but I can't. I'm sorry. I'm not starting at the bottom, but it's going up.
Yeah, it goes up to the reference.
Yep.
It goes up to the reference and goes down.
So as you go to the point of reference, it's going up. No?
Who can solve it?
Scott?
No, not Scott. This one.
So what you do is like that.
Go from the bottom and then it
Yeah, somebody from here. I like
You
this.
don't know this is.
Give him a G.
yeah.
No.
No, I'm wrong.
Check it out. Mr. Jonathan.
So you can see here, this V input here. So initially V input is negative, and this is larger than this. So this is larger than usually this is positive. This is larger than this is negative. And initially this is smaller than this. Should be output should be.
Wait, hold on, let me get
Yeah.
So
Yeah.
the minus
So
is
you draw a straight line up to this
the
saturation.
average is smaller.
This level, you see, this level.
No, you should have started from down there.
You go up to this one,
Oh,
then
unless.
it will go down.
Here we go. So
All
what?
the way down
He
until
was starting from the top way.
yeah.
But I asked him to start from the bottom and he said, yeah. And I'm like, okay.
Okay.
Other way around.
No.
Everybody
Start
clear?
on the bottom, now we're here.
Are you clear?
Yeah. No, if I see it was.
Because you see, this is this.
No,
This,
I did.
this is, remember, this is plus. If this is small compared to this, then this will be up. And if this is large compared to this, then this will go down. So initially your VE is negative here, which is much small compared to the reference. So that means The reference is on the positive terminal. So it will be up until you hit the reference voltage, and that will just go down and you hit again reset pi RC. Okay? Because it is more than Vref. Okay? So when this is more than Vref, it will go negative. When this is less than Vref, it will be positive. Because this has positive relation with the output, this has negative relation with the output.
Sweet.
If this is large, then this will go down. If this is large, this will go up. Okay? This has positive relation with the output, this has negative relation. So this goes high, this will go down. This goes high, this will go high. Okay? That's the relation. Okay? So this shows you what is the relation between these. Is it clear, everybody? Everybody clear? Okay? So we can take a break for 10 minutes.